Hi, this is Mr. Beck. This is Magnetism Lecture 4. Actually, we could call this Electromagnetism Lecture 4, but I forgot to put that in the title initially, so here we go. In this lecture, we are going to talk about a bar moving in a magnetic field, and what is set up in that bar. We're going to call that the electromotive force, and later on we'll give it a more familiar name. We're going to talk about a loop of wire moving into and then out of a magnetic field, and we're going to talk about what happens with that. We are going to introduce the concept of magnetic flux and see how that can help us solve some problems similar to what we've been doing with the electromotive force and the force on individual charges. Then we're going to talk about Lenz's law, which actually describes what direction a current is going to form in a loop of wire as it moves in and out of a magnetic field. And finally, we're going to say a little bit about the forces that occur when we have loops of wire moving in and out of magnetic fields, and that will tie together some of our mechanics with our electricity and electromagnetism. So join me. First, let's talk about a bar moving in an external magnetic field. In this case, I have a piece of metal top to bottom, and that metal bar is moving to the right at some velocity v. Now, as that metal bar moves to the right, that bar, of course, is going to contain many positive and negative charges. Now, of course, we know the positive charges actually stay in place and the negative charges move, but it's easy enough to just imagine that both the positive and the negatives move. Now, if you remember our right-hand rule for charges moving in a magnetic field, if we have a positive charge, so I'm using my right hand, a positive charge moving to the right, and a magnetic field, x's imply that the magnetic field is away from you, so I'll point that away. You'll see that the thumb is pointing in the upwards direction, and that means that the force on that charge, that positive charge, will be in the upwards direction. At the same time as the bar is moving to the right, we have a negative charge there, and for a negative charge, I would use my left hand. Now here, it's a little awkward, but I've got a charge moving to the right, a magnetic field pointing away, and that would result in a force in the downwards direction. So we're going to have forces on each of those charges in the upwards direction and the downwards direction. So the magnetic force will cause the negative charges to drift downwards and the positive charges to drift upwards. Now what we know is that there are a lot of charges in the bar, and therefore we're going to get a separation of charge. Now, just like a capacitor, when we have a separation of charge, we have an electric field, and when we have an electric field, that results in a voltage. But in this case, we're going to call that potential difference the EMF, the electromotive force. Yes, the same word we use for voltage, for potential difference, for electric potential, for EMF, it's voltage, so they're all kind of different words for the same thing in general. But in this case, we have an EMF, a potential difference developed between those positive charges and those negative charges that allows those charges to separate. So that's the potential difference, the electromotive force, and of course it's measured in volts. Now, the amount of electromotive force we get, which we draw as that curly QE, is going to be my electromotive force, E for electromotive force, and that curly QE, is going to be the result of the magnetic field strength, B, the length of the rod that's moving perpendicular to the velocity, and the velocity of the rod. So we have the magnetic field strength, the length of the wire or the rod in the field, and then the velocity perpendicular to the B field. So if this rod was moving straight towards us in the B field, in the same direction, sorry, if it was moving away from us in the same direction as the B field, then what you'd find out is that there actually is no EMF. So it's got to be crossing the field lines. It's got to be cutting the field lines in order to generate an EMF. Now, since there is a potential difference on that rod as it moves at a certain velocity through the B field, what we can do is connect that rod into a circuit and actually develop a circuit and a current in that circuit. So now that moving rod is actually acting like a battery of some sort because it has a certain amount of electromotive force or a certain amount of voltage. So if that either the rod is sliding on those wires to the right or that whole circuit with the resistor on the outside of the magnetic field, as long as this rod is moving to the right or this whole loop is moving to the right, then this portion of the rod, this rod is going to generate that EMF. The top portion of the rod is not cutting any magnetic field lines. So as that moves to the right, it's not going to be generating an EMF, nor is the bottom part of the rod generating an EMF because it's not cutting any magnetic field lines. And then the resistor is outside, so this branch is outside of the magnetic field, so therefore no EMF is generating there. So what we get is that magnetic field and the rod moving through it, the rod is generating an EMF, and then that will drive a current through that circuit. And so the current through that circuit, just like Ohm's law, V equals IR, so I is V over R. In this case, we use the EMF as our voltage source divided by the resistance. And the EMF is BLV, the magnetic field strength, times the length of the rod times the velocity. So we could have the current in the rod being the magnetic field strength, the length of the rod, times the voltage divided by the resistance. So all of a sudden we have, we've gotten back to electric circuits. Now, if we take a loop of wire and we move it through the magnetic field, what we're going to see is that initially, as the wire is on the outside, there's not going to be any current because it's not interacting with the magnetic field. As soon as that loop of wire enters in the current, then that front portion of the rod that is moving perpendicular and cutting the magnetic field lines, there's going to be an EMF generated in that portion of the rod. And so that EMF, if you use your right-hand rule, so here we have the rod moving to the right. The individual charges are moving to the right. Then I have the magnetic field that's pointing right towards you. You can see that the force on each charge is going to be pointed in the downwards direction. So the force is on the charges in the downwards direction, and that means I'm going to generate a clockwise current in that loop of wire as it is entering the magnetic field. Now, when that loop gets in the middle of the magnetic field, you see we could use our right-hand rule on both the front and the back part of the rod, on both this section and this section, and the right-hand rule will give you a force in the downwards direction on the charges in both of those branches of this loop. So if the forces are going to be equal, because the lengths are equal and the magnetic field is equal, then the force on each one of those charges is going to cancel out overall, so that I'm not going to get any current when the loop is when the loop is entirely within the magnetic field. Now, as the loop is leaving the magnetic field, now there's only that downward force on the charges on the back part of the rod, on the back part of the loop. So this part of the loop is experiencing an EMF, and it's driving the charges downwards. And there's nothing on the top and nothing on the bottom because those are not cutting the magnetic field lines. They're not cutting across the magnetic field lines. So there is no EMF on the top and the bottom or the right because the right side is outside. So again, we're going to generate a current, but this time it's going to be a clockwise current. And then once the loop is completely out of the magnetic field, then there's not going to be any current through around the loop anymore. Let's take a look at that again, but now we're going to graph the current, where a counterclockwise current is going to be positive, so it's going to be on the, up on the y-axis, and a clockwise current is going to be negative, so we'll put that down on the y-axis. And we'll do this over time as that loop passes through the magnetic field. So again, when the loop is outside of the magnetic field moving to the right, then I'm going to have zero current flowing through the wire. As soon as that front edge hits the magnetic field, then we're going to get a clockwise current, which I've called negative. As that front edge hits, it's going to start there. So that's right when the front edge hits the field. And then it's going to continue with that clockwise current, which we called a negative current, as it enters the field. As soon as that loop is entirely inside the field, then the current again is going to drop to zero, again because we have those forces in the clockwise and counterclockwise direction that are going to cancel each other out. So I will get zero current at that point. And then as soon as that front edge reaches the edge of the magnetic field, then what we're going to see is it's going to become a positive current. It's going to become a counterclockwise current because now only the back edge of that loop is experiencing a force, an EMF. And then finally, when that loop exits the magnetic field, when that back edge of the loop exits the magnetic field, then the current will instantly drop to zero. Now this, of course, is assuming a perfect magnetic field where there are no slightly growing and then slightly decreasing on the way in and out. This is instantly on and instantly off as the loop enters the field. But what we get is um, this stepwise current where it's negative and then zero and then positive and then back to zero as the loop enters and then exits the magnetic field. Now let's introduce the concept of magnetic flux. And its symbol is this Greek letter phi, or phi as some people call it, but I call it phi. So the Greek letter phi is the symbol used for magnetic flux. Now, if we think of the X's and the dots that we've been drawing on the page representing magnetic field lines, we can say that the density of the lines passing through a surface, or the number of lines passing through a surface, is going to be representing the magnetic flux. So the flux is going to be how much of that is actually flowing through a surface. The units of magnetic flux are called, I've heard these called Webers or Webers, and I'm not one to argue, so I'm just going to call them Webers. And you would get 1 Weber of flux if you had a 1 Tesla magnetic field strength and you had 1 square meter through which that magnetic field of 1 Tesla was flowing. That would be 1 Weber of magnetic flux. The equation for magnetic flux is BA cosine theta, where B is the magnetic field strength, of course. A is the surface area of that surface, surface that we're talking about. And then theta is going to be the angle between the magnetic field and the surface area. Now you might say, well, what direction is a surface pointing? What we have to do is we actually have to define the direction of a surface being what direction is perpendicular to that surface. So with my hand, it would be directly straight out from that surface. That perpendicular is the direction that the surface is pointing. So in our picture up above, the magnetic field lines are coming straight at you, and therefore the surface is pointing straight at you, in this case, parallel to the magnetic fields. So this area that I've drawn in the plane of the paper is facing directly at you, and therefore the cosine of the angle, if it's aiming directly at you, the angle would be 0 degrees, and the cosine of 0, of course, is 1. So you're going to get the maximum amount of flux when that surface when the surface is pointing parallel to the magnetic field, meaning it's in the plane of the surface is drawn in the plane of the paper, and the magnetic field is either coming directly out or directly in. Now, if you change the amount of flux through a loop, if you change the amount of flux through a surface, you're going to generate an electromotive force, an EMF. And so the rate of change of the flux is going to be equal to the amount of EMF or voltage that you're generating. So we can write that the EMF, that curly QE that we saw just before, is going to be the change in flux, or delta phi, over the change in time, delta t. So the rate of change, just like the rate of change of velocity is acceleration, so acceleration is change in velocity over change in time. In this case, the rate of change of flux is going to generate the EMF, and so that's the change in flux divided by the change in time. So there are 3 ways that you might change the amount of flux. One way would be to change the magnetic field strength. So if I start on the left and I have a certain number of dots coming through this surface, and then I show it changing to the right, if I reduce the number of dots, that's changing the flux through that surface. A second way to change the magnetic field strength, a second way to change the flux would be to change the area. And I can actually change the area in 2 ways. One, I might remove the loop from the field. That would change the amount of area that's within the field. So that would be a way to change the magnetic flux. Another way is I could change the shape of the loop. I could stretch the loop or make it bigger or smaller. So in this case, if I grab both corners and I pull out, I'm going to change the shape of the loop, leading to, in this case, less flux through the loop. And a third way is I could change the angle at which the loop is in the magnetic field. So if I take that loop from the top and I spin it around an axis, then I'm going to have less of those dots passing through the surface area. And if I spun it so that it got to be perpendicular to, so that the object was perpendicular to you, but the surface area was pointing directly to the right while the dots were pointing directly towards you, then I would have 0 flux through that loop on the bottom. Let's work an example problem. In this case, we have a 20 centimeter by 10 centimeter loop of wire with 0.3 ohms of resistance, which I've drawn as a 0.3 ohm resistor there on the left, enters a magnetic field of 0.4 Tesla in 0.5 seconds. So it's going to go from completely out of the field to completely in the field in half a second. What current is generated in the wire? Well, first, let's talk about the EMF. So the rate of change of the flux is going to be the EMF, and so that is going to be delta phi over delta t. The change in flux is going to be the final flux minus the initial flux. Well, the initial flux is 0 because the loop is outside the wire. The loop is outside the magnetic field, and then the final flux is going to be BA cosine theta. So I have BA cosine theta minus 0 over delta t. The magnetic field strength is 0.4 Tesla. The area is, since it's a rectangle, it's going to be width times height in this case. So it's 0.2 meters times 0.1 meters. Notice I turned centimeters into meters. Times the cosine of the angle between B and A. Now the area is flat there, in the plane of the page. I could say that it's pointing towards me, or I could say it's pointing away, and I'm just going to say it's pointing away at this point. It doesn't matter so much for the positive and negative for our purposes here. So I'm going to say that's the cosine of 0 because the magnetic field is into the page, and I'm just going to define that surface as into the page. So I've got 0.4 times 0.2 times 0.1 times the cosine of 0, which is 1, divided by the change in time, which is 0.5 seconds. Calculating that, I get 0.016, and the EMF is in units of volts. Now, what I was really looking for was the current in the wire. And so if I want the current in the wire, I have to use Ohm's law. So I have I is the EMF over R. It's the voltage divided by the resistance. So that's 0.016 volts divided by 0.3 ohms gives me 0.053 amps. So that is the rate of change of, that is the current generated in the wire because of that changing EMF. Now we have something called Lenz's law that will help us determine the direction of the current in the wire. And so Lenz's law states that a changing flux through a loop will induce a current in the loop. And that changing flux generating the current in the loop, the induced current will create an induced magnetic field that opposes the change in flux. That's a lot of words, but let's take a look at what that means. Here we have a straight wire with a current in it. And if we have our right-hand rule, our first right-hand rule, if we align our thumb up in the direction of the current and wrap our fingers around the loop of wire, what we're going to get is the direction of the magnetic field. And so it's coming towards us on the top of the wire, going straight down in front of the wire, going away from us underneath the wire, and coming back up behind the wire. Now, if we take that loop and if we take that length of wire and curve it into a loop and have the current flowing around the loop, what we can see is that we could apply a right-hand rule to each little section of the wire. We could grab the wire up on top. We could grab the wire here and figure out what direction the magnetic field is, and grab the wire here and figure out what direction the magnetic field is, and so on. So we could work our way around the wire. And if we do that, what we see is the current going in a clockwise direction. So I just took that wire and bent it around into a circle. But now I get my loops of current around that wire. Now, since it was away from us underneath the wire, and I curved the wire down to make a loop, then it's away from us in the center of the wire, and it's coming towards us on the outside of the wire. So you can see coming towards us on the outside of the wire, and then going away from us inside the loop. So if we convert those, into dots, what we see is that those loops became dots straight in the plane of the page coming towards us above the wire and X's going away from us underneath the wire. We can do the same thing with that loop. So what we're going to get is away from us on the inside and towards us on the outside. So we get the magnetic field as X's inside the loop and dots on the outside of the loop. Now what this does is it introduces a new way to think of a right-hand rule. What we can do is we can take, the third right-hand rule, I'm losing track. But we'll take our right hand, and if we wrap our fingers around the direction of the current in a loop, then the thumb is going to point in the direction of the magnetic field inside the loop. So if you grab onto a loop of wire and the fingers are wrapping in the direction of the current, you'll notice that the thumb is pointing away from you, and that away from you is showing the same as the magnetic field inside the loop. So that is another version of a right-hand rule. Now let's see how that plays out with a loop of wire entering a magnetic field. In this case, the loop of wire starts with no flux inside of it. And as it enters the magnetic field, there's going to be these field lines that it's going to have suddenly going through the loop of wire as it enters. Now the loop of wire is going to generate a current to counteract that that extra magnetic field. So if we see the loop of wire entering the magnetic field, suddenly that loop has more X's in it. So the loop wants to counteract that. And the way the loop counteracts that is it's going to create a current such that that current will generate dots in order to cancel out the extra X's that are now flowing through it. So if it has extra field into the page, it wants to generate a current so that it can generate a magnetic field out of the page to cancel out those X's. Now, if you use your right-hand rule, in order to get a magnetic field pointing towards you, you're going to have a current going in this direction, which for you would be a counterclockwise current that we're going to get as we generate that field. So the current is going to be counterclockwise to generate the dots. The dots cancel out the X's. So the way to think about this is that the loop does not like change. If it gets extra X's, it'll create dots. If it were to get extra dots, it would create X's. If it loses X's, then it would want to make X's to replace the lost X's. And if it loses dots, it's going to want to create dots to replace the lost dots. So another thing that's very important to see is that this is only while the loop is moving does this effect happen. So when it's standing still, there is no change in flux. So when it's standing still, it's not going to generate a current. So that will be the direction of the current as the loop enters or exits a magnetic field. And oh, this is the same result as you would get with a moving bar. So if you think about that moving bar that we had before, if we think about a charge, a positive charge in the front edge of this wire, as that positive charge moves to the right, then it's going to experience this magnetic field of positive, which is going into the page. So now I've got a charge that's moving to the right with a magnetic field, middle from magnetic, going into the page. That charge is going to want to be forced in the upwards direction, which confirms our direction of current as being counterclockwise in this loop. So yeah, the same result as a moving bar in a magnetic field. Now, we have something called a solenoid. A solenoid is not just one loop, but many loops of wire. So in this case, I've got a solenoid that I've tried to draw with a current coming down in the front, and it'll be down in the front of all of these loops. And then in the end, it goes down in the front, up in the back, and it escapes the loop. The current goes off in that direction. So that is going to be a solenoid. It's going to be many loops of wire, all connected together. Now, when I take a solenoid, if I wrap my fingers in the direction of the current, this is back to that third right-hand rule. If you think about the individual loops all adding together, then if I wrap my fingers in the direction of the current around that solenoid, then I'm going to generate magnetic field lines inside to the right in the case of this loop of wire, this solenoid. So the thumb will point the direction of the field inside the loop. That was our third right-hand rule. So you see it coming out of the right hand, going around and in through the left, and then inside the solenoid, the magnetic field lines are pointing to the right. So it's from the right to the left on the outside, and then inside it's from the left to the right. But again, the fingers wrap in the direction of the current, the thumb points in the direction of the field inside the loop. Now, if that looks vaguely familiar to you, it should, because if you look at a normal bar magnet, we have the same thing happening where we have magnetic field lines coming out of the north, going around and going into the south. And then within the magnet, we have the magnetic field lines going from south to north. What that tells us is that a solenoid with a current, an external current running through it, The solenoid will generate a magnetic field, and the solenoid basically is an electromagnet. So if you've ever taken a piece of wire and wrapped it around a nail and connected it to a battery, you can pick up paper clips with that because you have basically a solenoid and you're creating an electromagnet by running that current around the around in loops. That generates a magnetic field that acts just like a magnet. So a solenoid is going to act like a magnet, and what that means is that where the magnetic field lines are coming out is the north. So that means that the thumb is going to point north. So when you have a current carrying solenoid, you can wrap your hand around that solenoid and your thumb is going to point north as if that solenoid is an electromagnet. So what would happen if I take a magnet and I move it towards a solenoid that's not connected, that's just, loops of wire together? If I move a magnet towards a solenoid, then what I'm doing is I'm increasing the flux towards the right side of the loop. As I move the magnet towards the solenoid, these magnetic field lines that are coming out of the magnet are going to start going through the solenoid, so through the loops of the solenoid. Now, if I increase the flux towards the right side of the loop, then the loops are going to respond according to Lenz's law, and the loops are going to respond with opposing flux towards the left inside the loop. So I have more flux going to the right because of the external magnet. The loops themselves want to generate flux to the left in order to counteract the extra flux to the right. What that means is that the loop is going to create a north on the left side of the magnet, because if you think about the magnetic field lines coming out of the left side of those of that solenoid, then the left side of that solenoid will be a north end of a magnet. And this is an opposing north, because as the north comes towards the solenoid, the solenoid responds with a north back towards the approaching north. So as I move the magnet towards the solenoid, what I get is that temporary north-south, because it's only while it's moving will I see that those loops happen. On the other hand, if I take a solenoid and I have a magnet, if I take the north end of a magnet and I move it away from the solenoid, now I'm going to start with flux going from left to right in the solenoid, but as I move the north away, I will decrease the flux towards the right inside the loop. The loop will respond with increased flux towards the right inside the loop to replace the lost flux. So some of these magnetic field lines that are going into the loop right now will wind up being lost. So I have now some magnetic field lines going to the right. As I pull the magnet to the left, I'm going to lose some of those. So the loop wants to respond by replacing those lost magnetic field lines. So the loop responds with increased flux towards the right inside the loop. Now, if inside the loop the flux is going to the right, what that means is the right side of the magnet temporarily becomes north, because that's where the flux lines will be coming out, and the left side of that solenoid becomes a south, because that's where the new induced flux lines will be going in. So what that does is create a south, which would actually try to attract to the north that you're pulling away from it. So the current will be down in the front of the loop, and this only happens while it's moving. So let me do this animation once. Here it comes. The north moves away. It generates a temporary magnet with a south, trying to keep the north from going away. So this is interesting. As I take a magnet and I move it towards a solenoid, the solenoid becomes a magnet that opposes the motion of the magnet towards it. And the same thing happens if you try to pull a magnet away from a loop of wire or a solenoid. Then the solenoid will try to make an attractive force, keeping that magnet from moving away from it. So that is how Lenz's law acts in order to oppose any change. It actually creates a force, an attractive force, as you try to pull the magnet away, and a repulsive force as you try to push the magnet towards. And you can think about what would happen if you moved the south pole of the magnet towards and away from the loops of wire. You'd get a similar effect, where if you move a south towards the loops, then the loops would create a south to repel the south. And if you pull a south away, the loops would create a north to attract the south and keep it from going away. So this is only while the magnet is moving. Let's take another look at this problem that we did before. Before, we were just looking for the current in the wire as the loop went into this magnetic field. So we earlier solved for the current on the wire being 0.053 amps. But now I want to talk about the force on the loop. And so since we generate a current in the wire, now we have a current carrying wire that's in a magnetic field. So let's just hold on to the magnitude of that current. The magnitude of that current was 0.053 amps. And if we use Lenz's law, we can see that we're going to get a counterclockwise current. So now we're going to know the direction of that current. So again, since we have the loop is going into the magnetic field is X's pointed into the page. And so there are more X's in the loop. The loop doesn't like more X's, so the loop wants to generate dots. Dots are coming right at you, so that would be coming right at you, and that would mean that it would have to generate a current in the counterclockwise direction in order to generate dots coming right at you. And so I've drawn the counterclockwise current due to Lenz's law. So now I've got 0.053 amps in a counterclockwise direction. So now I have a wire in a magnetic field. And a wire in a magnetic field is going to feel a force. The magnitude of the force on that right side of the wire is going to be given by BIL, the magnetic field strength, times the current, times the length of the wire. So the magnetic field strength is still 0.4 Tesla. The current that we calculated was 0.053 amps, and the length of that right side of the wire is 0.1 meters. So we calculate that and we get a magnetic force of 0.0021 newtons. In what direction will that force be? Well, if we take a look at our right-hand rule, we know that the current is in the upwards direction. We know that the magnetic field is pointing into the page, so that would leave a force pointing to the left on that section of the wire. You could do the same for the top and the bottom of the wire, but since the current in the top of the wire is going to the left and the current in the bottom of the wire is going to the right, you should see that regardless of the length of the wire, how much of the wire is in the field, the magnetic force is going to be equal and opposite on the top and the bottom of the wire, so there's not going to be any net force on the entire loop. And on the left side of the loop, since it's outside of the magnetic field, there will be no magnetic force on that section. So the only magnetic force for the net force that's going to matter is on that right edge of the loop. So in order to maintain a constant velocity, in order to fight that magnetic force to the left, I have to push this loop into the magnetic field with a corresponding applied force to the right. So it actually takes some force to push a loop of wire into a magnetic field. And you could work it out where if I'm pulling the wire out of the magnetic field, the current would be generated in the opposite direction, and that would lead to a magnetic force in the opposite direction. And so the applied force, again, would be opposing the motion of the loop. So if the velocity is to the right, the applied force has to be to the right to maintain the velocity because the magnetic force will be to the left. And if I were to have a velocity to the left, then there would be a magnetic force to the right. So I would need an applied force to the left in order to maintain that velocity. So I have an equal applied force to maintain a constant velocity. Now let's just do an interesting thought experiment. Let's figure out what would be the amount of work required since I have an applied force and I have a certain distance to push that loop into the magnetic field. The work done by the applied force we can calculate simply with force times distance. So now the applied force is going to be 0.0021 newtons. The distance I would have to push that into the magnetic field to get the loop completely out to completely in is 20 centimeters or 0.2 meters. That means that I have just done 4.2 times 10 to the negative fourth joules of work pushing that wire into the magnetic field. Where did that work? Where did that energy go? Well, this is a circuit, so we actually can calculate the work done by charge rolling through that circuit. So the work done in the circuit is going to be the power of the circuit times the amount of time. The power can be calculated as I squared R. It could also be IV or V squared over R. But in this case, I squared R makes sense because we know both I and R. And the time there is half a second because I'm pushing it into the field in half a second. So if I take the current and I square it, 0.053 amps squared, times the resistance of 0.3 ohms, that's I squared R, times the time of 0.5 seconds, I get 4.2 times 10 to the negative fourth joules, which is remarkably the same amount. Actually, not remarkably, because energy is conserved. It had to go somewhere. So this energy that I use in order to push the loop of wire into the circuit actually is going to be released as heat from lost from the resistor. So I hope that was a good introduction to Lenz's law and to some of these concepts. Keep an eye out for what might be a lecture 5, where I'm going to work through a couple of problems.